Well, thanks everyone for joining me today. Today we were talking about scaling schema cardinality and how we're creating types at runtime. And you're probably wondering, what does that mean? So most GraphQL projects I've seen, they kind of take on one of these three formats. I'd say most kind of live in this space, which is I'm building a schema and it's unified. And so maybe I'm in a monolith with just a single schema, or maybe my schema is federated and I have subgraphs, but all my consumers, they just talk to this one type of unified schema. Or maybe I'm someone like Shopify, and I have a small set of schemas that I own. So one schema for the storefronts, and then one schema for admins, for example, I believe is their setup. So I do have to deal with different types and different schemas and different operations and fields within those schemas, but it's a small set of things that I can manage. The third type is those who bake their schemas. And so maybe I want to allow the users or the tenants of my system to define some set of types, and I'm going to make those types also appear within the API. And so there's going to be some process, either completely offline or kind of like regenerated at runtime, but I'm going to fully expand that schema and create a new schema representing and containing the types of my users within that schema. So broadly, I'd say, most projects are within one of those three categories, with the vast majority being within the first. Okay, so what if I have a different set of problems? What if I have an extremely large number of schemas, not even GraphQL schemas, but within my system of record, I might have a whole bunch of different types people will want to expose. Maybe I allow people to create types within the system. Those types can have different fields, and based on users' roles within the system, they may be able to see different sets of types. They may be able to see different sets of fields. And so if I think about wanting to represent all of those types, I actually have the problem of, okay, now I don't have one or three schemas. I could have millions or billions, potentially. And then what if I have some authorization concerns with the existence of fields as well? What if I have a type called employee and there's a field called is getting laid off next week, as I recently was? What do I do in that case? It's not even knowing about the data of that field, but just knowing about the existence of that field. That can be actually a security violation, and you don't want to expose it to different users. So what do I do in that scenario? What if we said that each type in the schema is either static or it's dynamic? All static types are available to all users, and knowing of their existence is never a security violation. Static types are available at build time. For example, the type int, just the scalar integer, that's always safe to expose for all users, and we can know about that at build time. There may be other more complex types like interface, object, or union that we can expose as static types. Really just depends on what your business domain is here. There's likely some set of static types that everyone can see. In addition, I'd recommend that all interfaces be static as well. And then there's a set of dynamic types within the schema. And those types will be lazily created, and they will represent types that the users may have control over within your system. When you're building a system like this, and again, probably the vast majority of us will never need to because this is tricky stuff and not fun, but you can ask, does user A have access to type X? And then given the result of that query, we may instantiate some dynamic type at runtime with that information. And then we can also say that not all types have the same set of properties exposed to the same set of users. So maybe I have a dynamic type with certain fields for certain users, and only managers can see that is getting laid off field. And most importantly, dynamic types, when we're creating them, still fully in compliance with the spec. We don't want to go outside of the spec. We don't want to get too crazy and require different clients and different tooling to use these kind of dynamic types, so you want to ensure spec compliance. Okay, so before we talk about dynamic types fully, let's just think about what we can do with static types. We can have a set of static types within the schema, but those static types, they can still have dynamic parts to them. So for example, we could say that, okay, there's a static object type that exists, but maybe it has some dynamic fields on that type. Possible types of a union, maybe some static possible types, but then maybe we say, okay, we allow users to create an object type, and one of those object types could potentially be a possible type of a union as well. Enum values, same thing, could have a set of static enum values, and then could extend those with dynamic enum values. And then finally, input object fields, again, could have a mix of static and dynamic input fields on each of these types. So here's an example of two object types. User A and B, they both see the employee type, and they see the same three subfields here, so ID, name, and birth date. User B has an elevated level of access within the system, and so he's able to see this, secret project field. And he's the only one who's able to see this. And so there's some affordance built within the system that determines, okay, we're dealing with the same type here, but we're actually adding a dynamic field for user B. Similar idea for a union here. User A, they see that I have some project union. Project A is this whole element of it. And because only user B has access to secret project, they only see its existence within that union type. Similar idea for enums here. Project A for user A, and then the secret project and project A for user B. And then finally, again, just showing an example of, here's an input object type, employee filter, some way to like filter employees within our schema, and they share the same set of input fields, but because user B has access to that secret project, they get an additional input field that shows, okay, I can now do filtering operations on that type. So those are examples of all static types that all users could see, but I can get different properties on those types depending on who I am in the system. Then we can make it even wackier, and we can say, all right, now in addition to static types, we have dynamic types. And what I'd recommend, if anyone is considering building a system like this, keep it to objects, unions, enums, and input objects. Those are likely the parts of the system that you'll want to let your users configure, and then interfaces, they can remain a contract between yourself and like your component developers or certain other aspects of your system. It's an interface, it's a contract, right? So when we're creating these types, it gets tricky, especially when we're thinking about how we want to do this in a spec compliant way. So how are we going to organize this? If you take a look at this example, this is just traditional SDL, right? We've all seen this a million times. Here's an example of maybe an extended SDL. The important point to get across here is that you may not like the syntax, and that's okay. You may not even have a truly extended SDL. The more important point is thinking about this as a concept. So you can see that, the user image type here, it's wrapped in these angle brackets. So what does that mean? So it means that it's actually a different type of type than what we would typically have in the SDL. And so what I've been using is the term category. And so kind of like a generic type in your programming language, you can say that, okay, I have these categories of types, and I may have types created at runtime that reside within the category. And so let's say that I'm building a CMS where some of my users, they want to call their images image, and some of my users, they want to call their images photo. I create the category user image, and both those types live within that category. Those two types are dynamic types living within the user image category. So that angle brackets is just kind of a way to convey that, and you also see that you still retain kind information. So you still see that it's an object type there. Okay. So categories allow us to talk about the types of types we have within the schema, and we want some mechanism to convey to the client that these are now categories we're discussing. So if you hate angle brackets, you can make it a directive. You can do whatever you want. Syntax is not really important. It's more about the concept. We can have these categories interleaved with the regular SDL, and then the client can build a graph of types and categories. And so when the client is working with queries, it may not know the exact concrete types that it's dealing with, but we can annotate those queries, perhaps using directives, to say that, okay, these are the types of types I'm working with, and I don't have as strong of a contract as I do with a fully set of static types, but I can see that, okay, maybe this type lives within the user image category, and I know I at least have something like width, height, and source on it. Okay, here, let's just walk through a little bit what an extended SDL might look like. So on the left, you can see my user enum there, and I have one static value, and then for my dynamic value, I just throw a question mark on there. Again, syntax not really important. The user type here, this is a category of object types named user, and there's basically 4 combinations I can think about when creating fields and field types on objects. So I could have the field name be static, and I can have the field type be static, or dynamic and vice versa, and you can get all basically 4 combinations. So the first one, just named ID, static name of type, ID non-null. So everyone's familiar with that. We all know what that is, 2 static parts. The second, and same for name there. The second one is followers, and you can see that the type there is user. If we refer back to the definition within our SDL, that's actually a type category. And so we don't know what the actual type will be at runtime, but we know it will live within that category. And so if I'm building a query, I would know, at least statically as a client, that if I go followers and then ask for ID and name, those fields will exist on that type. Third, we have a dynamic field. So likes, you can see again that there is a question mark there. So we may not know what that field is necessarily called, but we do know that it has a like connection type. So the type is static, but we don't necessarily know what the field is called there. And then finally, a zany one at the end, you can have a completely dynamic field with a dynamic type as well. And why are we doing all this? This can just be the case that we want to allow our users to configure certain aspects of our system, and it's totally up to us on how much configuration we allow there. If we want fully static field names just with configurable types, we can do that, or we can kind of get a little bit crazier. Union, again, just a union category, and then I can see that there's 2 possible things. Application, I haven't included the type definition, but just assume it's some like static object type. And then user, which we saw previously, it's a category. And so because we don't have like set size yet within this, we could say 0 to n things would appear within this, this union. And then, not to belabor the point, but user filter, again, an input object category here. Like object, you can have that kind of like 2x2 matrix of static and dynamic things. And so I can have static fields, dynamic fields, and then static field types, dynamic field types on each. And it's just going to depend on what your application is, where it makes sense to use those things. So, okay, let's say you're crazy like I am, and you say, yes, I want to do this. This represents a good idea for my system. What do I actually need to do to support a system like this? You have to fundamentally answer 2 questions. The first one is, what is all the dynamic types that are appropriate for a user? So that's getting the entire set of types. Of course, we can add additional methods to make it more efficient, but when you're doing something like an introspection query, you want to say, okay, here's the full set of types available for the user. And then secondly, for each type that I have dynamically created, what is the appropriate set of properties available on that type? So for example, what are all the possible fields on the object type? What are the possible types within a union? And so on. And so I want to be able to fully expand all properties of each type with the appropriate user context. You'll see here too that I'm just kind of giving the same argument for the context things, but again, you probably want to specialize that, but I'm just trying to make the slides a little bit more simple. Okay, so this is tricky to do well, I would say, and we want to be spec compliant, so how do we organize this thing? I'm going to walk through now the architecture of how I did it. I'm not saying that this is the best way to do it, but it did work well for us, and maybe there's ways that we can improve on it. So within the system, there's fundamentally 2 different sets of actors, what I call the type constructor, and then the type informers. The type constructor will be a singleton, likely on a per request basis, or within the flow of a particular set of user requests. And then the type informers, I'd recommend each type informer would own one category of dynamic types. So one type informer might own that user image type, for example. Okay, so what's within the type constructor? When we're building types and answering questions about the query for the GraphQL engine, because as the query comes in, we parse it, we validate it, we want to know about the associated types. That's the type constructor's job, to give that information to the GraphQL engine. So when a query is coming in, the engine might ask something like, okay, I have this type that's dynamic, and is there a field called ID that exists on this user type? In the metaschema, we remember that everything within that certain category of types, they had that static field ID. And so the type constructor, independently of any type informers, it's able to say, okay, based on the existence of this metaschema, I know that anything that resides within this category has this static field ID of type non-null ID. And so without even talking to a type informer, it can answer affirmatively, yes, that field exists. And so it'll hold a reference to this metaschema to answer questions like that. The type constructor is also going to hold a reference to all the type informers within the system. Because the type informers, they own one of the categories of dynamic types, the type constructor is going to be responsible for delegating to the appropriate type informer when it comes time to answer more questions about that type. The important point to note here is that if you ever do build a system like this, likely you'll have probably someone who's like very familiar with GraphQL and the spec. That person should be responsible for owning the type constructor, because that's where you ensure spec compliance happens. But you're probably going to have, again, probably a GraphQL expert, but maybe people who are less familiar owning type informers. And so you want them to be able to answer what types ought to be constructed, but handle the actual type construction itself within the type constructor, because that can do it safely, and all type construction happening in one place ensures you're spec compliant at all times. So the type constructor is how things get constructed, and the type informer is what things ought to get constructed. Okay, and then lastly, the type cache, that also lives within the type constructor. So oftentimes when you're parsing a query, you're kind of going through and seeing like a similar set of types again and again. Some of these type construction, like what ought to be constructed, some of those methods, they can be expensive. And so you want to memoize the result of those computations, put them in your type cache. And so the second time that question is asked, does field X exist on type user, you can just reuse the result of that previous computation. You're not going back to your type informers and asking it the same question again. Okay, all type informers, they should have at least two methods. The first one is, does some type exist within that category? So you could say, does type photo exist within type user image? And it's going to give you back one of these type references, which you can use to instantiate types. And that's going to be really useful for the _type field. When you're doing an introspection query, that's when you'd use that field. And then the second method is get types. So this would be to say, all right, for a category of types, fully instantiate all types that reside within that category, and then give me a reference back to all those types. That's useful when you're querying the _schema field. You're going to iterate through all your type informers and say, give me all your types, give me all your types, and then that whole set in combination with the static set of types is what's returned as part of the introspection query. So those two methods should exist for every type informer. You can kind of even get a little bit more efficient. It can be a little bit expensive to say, okay, do you own the poster filter type informer? And it'll say no. How about you, type informer? Do you own it? Okay, yes, I do. What you can do is say each type informer has some namespace parts, literally just an array of strings. And then if a type name doesn't have that full set, then it means that that type informer would never own that type, and we can skip asking it that question. And we do that because sometimes it can be really expensive to go to our system of record and say, okay, does some type exist within this context for this user? And we can just skip that entirely based on substrings. This would be a great reason why if we could get namespace support, it'd really help us in this, because we can just assign a namespace to a type informer, and we don't have to iterate through those all at one time. Okay, and then I lied. It's actually even more complicated than I said before. So there's one base type informer interface, and then based on your type kind, you want different methods for each of those type informers. So one for enum, union, object, and input object. And that's because each of those kinds has different properties, and so you want to ask different questions based on the type kind. So enum, it's the simplest, just saying, does some enum value exist for this type? And again, here you can see that the context argument, it's repeated, but you don't want to specialize it in practice for the type of question you're asking. Union type informer saying, okay, I have some dynamically constructed object type, and is it the case that this type resides within the category for this union? The object type is where things get fun. You can see that there's kind of a split here. You have the has field and has argument methods, and then the field type and argument type methods. The reason there's a split is that it could be the case that I have a dynamic field with a static type, and so when I'm asking, does this type have this field, the type informer can say, yes, it does, and it resides within this field category. That field category can have a static type, and so I don't have to ask the type informer again, what type is that? I know based on the field category what the type is, and so I can basically just return a reference to that type already. So you're not always necessarily asking both questions. But if it is a dynamic type, it'll go back and say, okay, for this field, what's the actual type? And then it should return the type for that. And then input object, kind of similar. Oh, I should call out too that you might also want to have dynamic arguments as well. So like where I encountered this was when you're filtering and ordering things, we created arguments for those kind of operations. And so you want your argument types to be created specifically for the source type. So I might have a type called like user, and then I want a user filter type, for example. Input object's a little bit simpler than object types, just asking, does some input object field exist, and then what is its type, if so. And again, similar kind of like pattern to objects, how you don't necessarily always need to ask that second question. Okay, so within the type constructor, we have this type cache, and there's going to be what I call type references. There's going to be three things that are similar across all type references. You're going to have the name, which is the actual instantiated instance name of the schema part. So for types, this is the type name. For fields, this is the field name, and so on. The second part is a reference to the category from which that schema part resides. So if it is an object type, I'm going to point out the object category that it lives within. The reason why I'm doing that is because when I need to ask more questions about this object, I can go back to the appropriate object type informer and ask that type informer directly. The third thing is what your GraphQL engine is going to care about, the actual schema part here, so like the GraphQL object type or the GraphQL input type. Again, we want to hide this whole thing from the GraphQL engine, and so we just want to return back those concrete types to the engine while it's validating so that it doesn't really have to care that all of this is happening in the background. And then, yeah, you can see just, we can associate the type references with the appropriate type informers. Okay, this is what I call my DoD slide because it's messy, but this is a full end-to-end example of how this might work. So this is your GraphQL engine on the left here. So for example, something like GraphQL Java. Its responsibility is to take the query in, parse it, validate it, and then call the resolvers in the appropriate order. So this is all happening during that validation step where I have the AST of my query. Now I want to associate all my AST nodes to my actual types within my schema. So the first thing that happens is that it says, okay, does some type exist? And it's going to look at the fully instantiated set of dynamic types, and it doesn't find a type in there. So it's going to delegate that process to our type constructor, and it's going to ask, hey, do you have some reference to whatever the type is named? The first thing the type constructor is going to do is it's going to say, okay, is it one of those static types that may have some dynamic parts that I actually own? And so it's going to go into the metaschema, and it's going to say, all right, does that type exist? In this case, we're saying, no, we can't find that type, and so we just give back empty for optional there. Next, the type constructor is going to say, okay, I'm going to iterate through all of my type informers, and I'm going to ask it, do you own this type? Do you own this type? And finally, we do eventually hit upon one type informer that does own that type, and it's going to give us back an optional full of type reference there. So we found one type informer that declares, yes, I own this type, and it's within this category. And so we get back a type reference to the type constructor. Type constructor says, great, I'm going to take that type reference, and within the type reference, I know the name of the type and I know the category of it. So I'm going to create basically this cached object that has those two properties, and then in addition, it's going to create the GraphQL object type for that type reference. That GraphQL object type is going to be returned back to the engine, and then it's basically the same as if the engine was looking at like some map that you had within your static schema and said, oh, I did find the GraphQL object type for this. Okay, we continue parsing the schema, and we say, okay, does some field exist on this type? It's not a static field, it's a dynamic field, and so we're going to go back to the type constructor and say, does this field exist? The type constructor now knows what type informer owns that type, and so it goes directly to that object type informer and asks, does this field exist on this type? The object type informer answers affirmatively, yes, that field exists, and it gives us back the field reference there. We're going to mutate the cached instance of that object type to add that field onto the type. Again, I keep track of the name of the field, the category, and the actual GraphQL field type that'll return to the engine. And we mutate the cached object because if we're going to ask that question again, we can now just return back a reference to the thing we've already built. We don't have to ask that question for the second time. Okay, and then finally, that GraphQL field is just returned back to the engine, and the engine just keeps plugging away, processing the query, and so on. Okay, if you do want to do this, there's a few things that I'd recommend we think about as a community. The first two are for library authors. And so as you saw in that previous slide there's this process of while we're validating, there's this delegation between lookups of types from the static set to the dynamic set. And so it would be great if library authors gave some facility for people who want to do this to basically plug in a type constructor, and then the delegation could happen that way. If you're a library author and you've created all of your types as concrete objects and you want them fully expanded, it's not a great fit for these types of systems. Some of the things that I've worked on, you can have 1,000+ fields on the type, and it's just not smart to fully expand that. It's just going to kill your latency when you're processing your queries. I basically just want to create lazily the only parts that they need, and then return those back. And so please create whatever GraphQL objects that you're working with, or type kinds I should say, as interfaces, because then I can just conform to that interface and just give you the parts you need as opposed to the fully expanded thing, GraphQL Java. And then the last part is for spec authors. If you don't totally hate me after this, if we got namespace support, as I said, we could then associate dynamic type categories with their namespace, and then we wouldn't have to iterate through type informers when we're doing type instantiation. That would be super useful. And so if we ever land namespace support, we could associate each namespace to a type informer. Okay, thanks everyone. Really appreciate it. And yeah, if there's any questions, be happy to listen to those.
If anybody has questions, there's a microphone at the table.
How long does that cache live? Is it just per request, or?
Basically, like you might find in your system that, like, let's say you're doing a batch endpoint, you might want to keep it alive across that batch set because you're still operating within that context of that particular user. But usually, probably yes.
Can you elaborate on a little bit more on your namespace, the very last point that you made?
So if we go back to this, let's say I have a type like here called poster, and I want to say what type informer owns that type. Let's say I have 20 type informers. I have to basically iterate through each type informer and say, do you own this type poster? Do you own this type poster? And maybe one of them finally says yes. We can basically hack and support for a limited form of namespacing where we say, okay, this type informer declares that all types it owns always has the substring filter within it. And so because the word poster doesn't have filter within it, we can skip over that type informer, and we don't have to ask it that like potentially expensive question. But if we did have the namespace support, and we could say, all right, this type informer owns this namespace, then when we're working with a type, we know the namespace of the type, and we can basically just directly go to the type informer that owns that type without having to iterate through them all. So basically just a more direct way of asking type informers what types they own. Does that answer the question?
But GraphQL doesn't allow you to have a namespace. So for example, poster, right? Even if you have 20 type informers, you can only have one poster. Is that right? So how do you deal with this problem where poster may be duplicated in 2 different type informers?
Yeah.
Just not sure whether you have that kind of problem at all.
Yeah, correct. Like, it doesn't have namespace support today, but it's basically one thing that's been currently discussed is like, can we add namespace support to GraphQL? Yep.
Yeah, one question. When the schema is dynamic and the types can be added on the fly, and with the fields added to the types, so how does a client go about consuming those types, consuming the schema?
Same way. It's fully spec compliant, so you can just send your query up to the server. It's parsed, it's validated, it's executed, and then it's returned back to the client. I think where it's maybe a little bit tricky is that when you're building your client-side tooling, you can have some field that truly does exist on the type for that particular user, but you can't statically, based on just the static schema alone, know that that is like a valid field that you're querying. So one, you can just do an introspection query and get the fully expanded schema for that user and then validate based on that, but maybe that's too expensive for you. Or two, you can annotate that field with a directive that says that this field lives within this category, and then that will give you not as many guarantees as a fully static field, but it will give you some guidelines on what the user can do with that field, and you'll know its kind as well.
I see. So does it mean that as a client, I need to dynamically construct my query?
Not necessarily. The queries can be fully static if you want.
But so let's say there is a dynamically added field. I may be interested in that field. So, but I don't know for sure if that exists or not.
Yeah, you can like, often within these systems, there's some way of asking the system, does this thing exist? So that's one method. Or you can just do a full introspection query and get the fully expanded schema for that user, and then just it's regular kind of GraphQL stuff at that point.
Oh, okay. Okay. Thank you.
Hey, yeah, thanks for this presentation. It's really interesting. So what I was wondering about is the execution model that you kind of outlined. We basically have a call to the system of record per dynamic field or type.
Yes. Yeah.
Have you considered an approach where you would essentially like pre-parse the query so that you would know, what information you needed to load from the system of record? And then you basically have like a meta GraphQL API, and your GraphQL API loads your GraphQL schema, if that makes sense.
You definitely can do that, and like it's just going to depend on what your system of record can do. Certainly that would be a great optimization. One thing that we encountered is that you don't necessarily always want to fully expand that, because we can have literally thousands of types, each with thousands of fields on them, and so just loading all that in one time per request, that would also be kind of a negative performance-wise, but it just kind of depends on what your system does. But yeah, it's definitely an option.
Makes sense. So if the query, you'd basically load the metadata required for a single query, I guess.
Yeah. Yeah.
Gotcha.
Hey, thank you for the presentation. I had a question around, so from what I understood, you essentially do all that at GraphQL query execution, right? Not a GraphQL instance building, right?
Like the schema building?
Yeah, like the
Correct.
schema
Yep.
and then GraphQL execution, yeah, instance. Yep. Okay, so what do you said you're using GraphQL Java?
Yeah.
So what do you hook into to do this essentially? Because so usually the way you do it, like you have your SDL or you do your programmatic schema building, and then you do build, and you do your runtime wiring, you have all your resolvers attached, And now, like, all the schema validation happens then, right? Not at the GraphQL query execution. So how are you able to hook in there?
It's a great question. So basically, I forked the library, and
Okay.
and whenever like some sort of schema property lookup happens, I basically gave myself the opportunity to delegate to the type constructor.
Okay, and so just follow up on that. So that's why you were saying the type constructor, like GraphQL spec compliance, you basically have to do it yourself, right? Every time you have to find, okay.
Yeah, like, so for example, like one thing you could run into is some type might exist for a user, but because of the permissions of your system, maybe no fields exist on that type. So
Right.
you can't really answer in the affirmative that that type exists because you're no longer spec compliant at that point. So it's one of the things you have to think about when you're in the type constructor.
So yeah, so like fragments and everything, all the like fragments on the type, and then you could basically construct a completely invalid query with a fragment that is not on the like parent type, and then you would have to revalidate every time, right? Like
That I'd say is a little bit different because that
Okay.
should be basically, there's validation rules for both the schema and for the query, right? And so let's say I'm defining some fragment where I'm querying fields on a type defined by the fragment that just don't exist. I can have a perfectly valid schema, but the query itself is actually invalid at that point. And you don't really have to worry about that because that is like, it's one of two things. One, you just wrote a bad query, or two, the client is assuming some sort of invalid set of privileges within the system, and they're asking for fields that they believe should exist, but don't in reality. And so you just have to basically plan for the second one and say, like, what's the way I can safely construct queries?
okay, interesting. Thank you.
Okay, I think we're out of time. I'll just be out in the hallway if there's anything else, but yeah, thank you, everyone. Really appreciate it.